Hi, everyone. My name is Oussama. I'm a PhD student at the IOR department at Columbia University, and today I'll be presenting our paper called Matching Drivers to Riders, a Two-Stage Robust Approach. This is joint work with Omar Housni from Cornell Tech, Vineet Goyal from Columbia, and my advisor, Clifford Stein, also from Columbia. I'll start by presenting some motivations behind our work. And the problem of matching demand to supply on a dynamic basis arises as an important problem in different fields. For instance, matching ride requests to drivers in ride-sharing platforms, or matching food requests to deliverers in online food delivery, but also matching search queries to advertisers in sponsored search. So all of these need to be, all of these matching decisions need to be dynamic, incorporating future demand as time goes. So for some of these sectors, sometimes there's the possibility of having a little wait time between the time the demand manifests and the time we need to make the decision. So when this sort of latency is allowed, a more efficient decision can be made through what's called batch matching. That is, instead of considering every request by its own, aggregate nearby demand into a group that we call batches over small periods. So that is from seconds to 1 or 2 minutes in ride sharing, for instance. And once we have this batch, optimize the matching decision over the whole group instead of just optimizing over the last request that joined the system. So as we can see in the picture, for instance, instead of matching the first request to the closest driver before observing the second one, we can wait a few seconds or a few minutes such that we get the two requests simultaneously, and then we can make a decision that will optimize over the whole group, therefore reducing the total wait time. However, doing this batch matching myopically without considering how the future batches will look like can be highly suboptimal and can result in bad outcomes for the future batches or the future subsequent demand. That is the main question that motivates our research, which is how can we use partial information about the future demand to make better overall matching decisions? And our work is part of this stream of research in the sense that we study a two-stage framework for matching problems where the future demand is uncertain and is modeled as a set of possible scenarios that can manifest. And these scenarios are specified either explicitly or implicitly. These two terms will become clearer as we go in the presentation. So I'll just go and lay the dynamics of how the model works. So we have a bipartite graph, and the vertex set of this graph is split threefold. On the left, we have a set of drivers, D, and on the right, we have the set of riders, and the set of riders is split into two. We have R1, the set of the first stage riders, the riders that we have on the system, and we need to match immediately, and R2, which is the set of the possible second stage riders that will come in the next phase of matching. They can only come from R2. So we have R1, R2, D, the set of drivers, and we also have a distance function between every driver and every rider from either R1 or R2. And we further assume that this distance between drivers and riders satisfy the triangular inequality. So how the model works is that we first observe R1. We need to immediately match the riders in R1 to some of the drivers in D. That's the blue decision that we need to make in the first stage. Once we make this decision, there's the second batch of K second stage riders from R2 that will manifest, and then will need to be matched to some of the remaining drivers in D. So this second batch of K second stage riders will be called the scenario, and we will use S to denote it. We have a parameter K that denotes the maximum size of a scenario, and we assume that scenarios can come from a predefined set of possible scenario, that's capital S. And S can be either specified explicitly, that is, we can provide what the scenarios look like one by one, or it can be specified implicitly by saying every set of riders from R2 that's with a cardinality less than K is a potential scenario, and that will be that second stage uncertainty. So once the second batch of the case second stage riders or the second stage scenario manifests, it needs to be matched to some of the remaining drivers. That's the green decision that we see on the screen. And our goal is to minimize the sum of the first stage matching cost, this cost of the blue decision, plus the worst case matching cost of the second stage over all scenarios, not only the one that manifested, but all the one that could have possibly happened. For the purpose of this talk, our first stage matching cost will be the weight of the highest edge of the matching between R1 and D. We will call this the bottleneck weight or the bottleneck matching. And the second stage matching cost will also be the weight of the highest edge of the matching between A scenario and the remaining drivers in D. This is also bottleneck matching. And the second stage cost will be the worst bottleneck weight of all the matchings between all the scenarios and the remaining drivers. We study other costs in the full version, namely the sum of the weights in the matching instead of the highest weight. And all the results that I will present in this talk remain true if we change the first stage matching cost to be the sum of the weights instead of the highest weight. Now I'll present the IP, the integer program that describes the two-stage robust bottleneck matching problem, where the two costs are the first stage cost and second stage cost represent both the bottleneck weights of the matching. So we want to minimize the sum of the two costs. The first stage cost is this maximum here. The first stage decision is Xij, where I stands for drivers and J is for first stage riders, R1. So we want to maximize the highest weight of this matching, which is the maximum of the IJ, Xij. The first constraint simply says that every riders in the first stage needs to be matched. The decision variable for every scenario S is denoted YS, such that for every scenario, the second worst stage cost is bigger than the bottleneck weight of the matching of this scenario. So that's why our matching problem is robust, because we take in this second stage the worst case cost. And so Yij for scenario S denotes also if driver I is matched to rider J and S. And this constraint, the fourth one, is very important in the sense that for every scenario, we can only use the drivers that have not been used to match a first stage rider. So this sum needs to be always less than 1. And this constraint just validates the fact that every riders in the scenario S needs to be matched to one of the drivers. So for the rest of the talk, I will use opt1 to denote the cost, the optimal first stage cost in the optimal solution. And accordingly, opt2 will be the second stage cost of the optimal solution. That will be handy in characterizing the approximations of our algorithms. Our contribution in this work is to first introduce the two-stage robust framework for matching problem that I just introduced in the previous slides. We also show and present hardness results for both types of uncertainty, either explicit or implicit. For explicit uncertainty or explicit scenarios, we present a 5 approximation to our two-stage problem with only 2 scenarios, and we present big O of P to the 1.53 in general for P scenarios. This implies that for any constant number of scenarios, we have a constant approximation. When the uncertainty is specified as an implicit list of scenario, we present a big O of 1 approximation under some conditions between the demand and the supply. So in a nutshell, our hardness result goes as follow. If our scenarios are presented explicitly, then the TSRMB, the two-stage robust matching problem, isn't hard, even with 2 scenarios. And as soon as the number of scenarios goes beyond 3, there's no 2 approximation unless P is equal to NP. Same thing goes for the implicit model of uncertainty. Even when the size of every scenario is equal to 1, that is K equal to 1, there's no 2 approximation for the TSRMB unless P is equal to NP. So knowing that the problem is hard and knowing that it's harder to approximate within a factor better than 2, we recourse to try and find in constant approximation for different settings. And the first easy setting is when we have only one scenario. In this case, the problem can be solved in polynomial time. And the main observation is that since the second stage cost is a bottleneck cost, the highest weight, then the value of the optimal second stage cost is one of the edges between R2 and D. So what we can do is we can iterate over all the possible values of the second stage optimum up to, and for every possible value, we just get rid of the edges with higher weights and set the other weights between the scenario and the drivers to be equal to 0. And then this reduces our two-stage problem to just finding a minimum weight matching between D, R1 and the scenario S with the new weights. So once we know how to solve the problem with one scenario, we consider the two scenario setting, which we prove to be NP hard. And what we show here is that with two scenarios specified explicitly, there exists an algorithm that yields a 5 approximation, or more accurately, solution with cost less than opt1 plus 5 opt2. The idea is in the proof is similarly, because the second stage optimal cost is the weight of one of the edges, then we can iterate all over the possible values of opt2, and without loss of generality, we can assume that we know the exact value of opt2. Once we know that in the second stage, if there's a pair of riders I from the first scenario and J from the second scenario, if I and J are served by the same driver in the optimal solution, then they should be within a distance of 2 opt2 to each other. So if I is served by a driver, then he's at the distance opt2. And if S1 is served by the same driver, then the distance between S1 and this driver is also opt2. So the distance between I and J is less than 2 opt2. And therefore, because I and J are served in the optimal solution by the same driver, they are close to each other. And then we can use only one of them to represent both. And in that case, we can consider a single representative rider for each such pair of close riders. Now, it is not easy at all to guess all the pairs that are served by the same drivers in the optimal solution. But one way we can approximately achieve that is to compute the representative riders by solving a maximum cardinality matching on S1 and S2, where all the edges that are considered have weight less than 2 opt2. So we compute a matching between S1 and S2. And then we collapse both scenarios and we construct a single representative scenario by having S1 as well as all the other riders from S2 that have not been matched by our maximum cardinality matching. And once we have only this representative scenario that's constructed by S1 and the unmatched riders of S2, we construct a matching such that every rider in this representative scenario is matched within a cost less than opt1 plus 3 opt2. And then the way we go back to the solution for our two scenarios is that the riders that have been matched in S2 can be matched with an extra cost of 2 opt2 simply by using the same drivers that we have used to match their mates in S1. So that's an extra cost of 2 opt2, and therefore the total cost of opt1 is equal to less than opt1 plus 5 opt2. The main part of the proof is to show that there's a matching between R1, our representative scenario, and the set of drivers with a cost less than opt1 plus 3 opt2. Once we show through construction that such a matching exists, then we can just use our algorithm for TSRMB with one scenario to get a matching that will have even a smaller cost. So how do we construct such a matching? First, we look at all the first stage drivers, R1, and we simply, for each one of them, we match it to the driver that corresponds to it in the optimal solution. So the first stage cost of this matching will be exactly equal to opt1. Next, we look at the set of the unmatched riders from S2, that's S2 unmatched. And we look at the part of S2 unmatched that contains riders that are far from S1. So rider whose distance to S1 is bigger than 2 up 2. These riders cannot share any driver in the optimal solution with any rider in S1. Otherwise, their distance to S1 would have been less than 2 up 2. So these riders are also safe. We can simply match them to their driver in the optimal solution. Now, for the second part of S2 unmatched, which contains riders whose distance to S1 is less than op2, but who have not been matched in the previous step. These riders are risky because they can share a driver in the optimal solution with a rider from S1. Let's take one example. Let R be a rider in S2 unmatched that is close to S1, and suppose R shares its optimal driver with a rider S from S1. Now, because R has not been matched in the previous step, that means that S has been matched to another rider in S2 match, let's call it T. And the way we proceed with our construction is we simply match R to its optimal driver in the optimal solution, and we match S to the optimal driver of T. So because R and T are both part of S2, their optimal drivers cannot be the same. So R and S end up having different drivers. And the second stage cost for all of this is less than 3 op 2. So that's because the distance between S and T is less than 2 op 2, and the distance between T and its optimal driver is less than op 2. So the sum is less than 3 op 2. So we prove that we can keep iterating like this. That means whenever we find a rider in S1 for which we have already used the optimal driver, we can simply go and look at its mate in the matching of the previous part and simply give that rider of S1 the optimal driver of its mate, and all of that happens with a cost less than 3 op 2. So this shows the construction, and in the previous slide, I showed how the extra cost is less than 2 op 2 to match the remaining drivers of S2 match, and the final cost is less than 5 op 2. We use this idea and generalized it to deal with a list of P scenarios for any number of P. What we show is that the same logic can yield a solution with a total cost less than big O of P to the 1.59 approximation for the TSRMB with an explicit list of P scenario. So the idea is to recursively process pairs of scenarios and combine them until we only have one single scenario. So if we start with 8 scenarios, just like in the picture, the next iteration will contain, next iteration will only contain 4 scenarios. And how we do that is that each step at iteration I, we match or we collapse scenarios together with a distance less than 2 times 3 to the I minus 1 op 2. And since we start with P scenarios, the number of iterations we need to get down to one scenario is equal to log 2 of P. And what we show is similarly to the 2 scenarios case is that at each iteration, we lose at most a factor 3 of the optimal cost, so that the final approximation is equal to big O of 3 to the log 2P, which is equivalent of big O P to the 1.59. So that is the idea for the P scenarios. Our third contribution in this paper is to present a constant approximation algorithm for the TSRMB problem with implicit uncertainty. So just a quick reminder, in the implicit uncertainty model, we no longer have a list of scenarios, but we only have the input K, and basically any subset of second stage riders with cardinality less than K is a possible scenario. The challenge with implicit uncertainty is that the number of scenarios can be exponential, and the consequence of this is that even computing the worst case second stage cost for a fixed first stage decision, even that might not be possible in polynomial time, because that would be taking a maximum over an exponential number of scenarios. Technically, the consequence is that we can no longer assume, like we did for 2 and P scenarios, that we can guess the value of op 2 and operate as if that's a given. In the case of implicit uncertainty, we show that our analysis depends on the balance between supply and demand, or drivers and riders. And In practice, that translates to introducing the notion of surplus L, which is equal to the number of drivers minus the number of first stage riders minus K. And basically the surplus is the excess in the number of available drivers for matching the first stage riders and second stage riders. In other words, the surplus is the maximum number of drivers that we can afford not to use to match any riders. And we focus on the case of small surplus. And just for the interest of time, I'm only going to present a basic case here in which the surplus is equal to 0. So when L is equal to 0, the number of drivers is exactly equal to the number of first stage riders plus the size of a scenario K. In this case, we show a 3 approximation by simply taking any scenario from the possible scenarios of size K and solving the TSRMB with one scenario on it. The idea is that because there's no surplus, all the scenarios in the optimal solution are matched to the same K drivers. That means that between any two scenarios, there exists a matching where all the edge weight are less than 2 opt2. Therefore, by solving TSRMB on one scenario, we get a solution that's less than opt1 plus opt2, and then we can transform it into a solution for any other scenario by losing at most another additive factor of 2 opt2, making the whole approximation opt1 plus 3 opt2. So the general result that we provide for implicit scenarios uncertainty is that there exists an algorithm that yields a 17 approximation for the problem when the size of scenarios K is less than the square root n over 2, where n is the number of potential second stage rider, and also when the surplus L is less than the size of scenario K. So those technical assumptions are needed for the proofs, but they are not restrictive in the sense that they still capture the regime where the number of scenarios can be exponential. So if K is equal to the square root of n over 2, then the number of scenarios is exponential. We cannot assume that we know the value of opt2, but even in this case, we show a 17 approximation. I'll stop the presentation here, and I'm happy to take your questions.